Sure. Recording in progress. Okay. Then welcome back, everyone, from the lunch break. Very nice. We continue with a lecture, and it's my pleasure to introduce the speaker, Giovanni Delgaldo, who's known to me because we've known each other for a very long time. But I mean, first and foremost, it's a funny coincidence because there's two Giovannis in the room that studied in the same university. So also Giovanni studied in Politecnico di Milano, telecommunications engineering, and then came to Ilmenau to do a PhD on minor channel modeling in the communications research lab in 2007, the same lab I joined in 2006 to do my PhD there. So for a short period of time, we were PhD candidates in the same lab. Then Giovanni went to Erlangen to join Fraunhofer IIS to work on audio watermarking and spatial audio coding. And he came back to Ilmenau in 2012. Since then, he is leading a joint research group composed of a department at the Fraunhofer IIS and a chair at the university, at Ilmenau University of Technology. And the research direction is electronic measurements and signal processing. Though today, Giovanni will not talk about his home field, electronic measurements and signal processing, but machine learning instead. Why is that? Originally, when we wrote the proposal, we had a lecture planned by Professor Ahmad Osman from Fraunhofer IZFP, who is an established researcher in the area of machine learning for non-destructive testing. But unfortunately, he became unavailable because he's busy with many other things. So I was desperately looking for another solution. And fortunately, Giovanni jumped in, and therefore he will give the lecture today, even though it's not necessarily his home field, but still, I think Giovanni feels confident to talk about machine learning today. And therefore, I'm very glad that we got you. And yeah, looking very forward to what you have to say.
Okay, thank you so much, Ferner, for the introduction. Very kind. Yes, so as you can see, there's quite a long list of people on this slide. That's because I basically copied a lot of material already available to me and had discussions about the material, so that's why it's that. But let me give you a little bit more on my list of sources. Right, so as I just said basically, then also quite good, and that would be also the reason why I talk about it, so that you can take it as a starting point for yourself. I believe this is a really good course, Introduction to Deep Learning from MIT, and it's completely available on YouTube. Then there's also a really, really nice work from the guys in Stanford. So there's this Human AI something center they open there. So every year they come up with a report, and that's a really big document, like 300 pages long or so. And they do a kind of a scan of what's going on in AI. And there's lots and lots of plots. I have some of them in my presentation as well. That's also a really good starting point to see what's going on. Another couple there. And also I would like to mention that I was almost about to put ChatGPT as one of the authors, because in this case, ChatGPT-O was really useful to me to develop the ideas or my ideas for the lecture. So basically what was going to be in the lecture and what not. And for the first time, I actually had a lot of interaction with the ChatGPT or with the chatbot. Something like it, just imagine, like you say, okay, oh, I was thinking, so I'm doing this. First of all, you have to give a lot of context. So I'm giving a lecture, and this is the audience, and this is the time frame, and some more details. And then basically I start discussing things like, okay, I think it would be good to have this, this, and that. What do you think? And the chatbot replies. And then I basically keep going basically back and forth. And I was amazed to see how an automatic tool could, in some sense, replace maybe even other humans. So I would suggest to you to have as much interaction as possible with each other and with the scientific community. If I think about my own life as a scientist, this was the number one factor that made me grow in what I am today. So this interaction, so going to conferences and discussing about other people's research and getting feedback to yours is so essential. And having an automatic tool to, let's say, augment this experience, I think is great. So that would be a suggestion. So, DALL-E is for making pictures. You will see some of them. And then, of course, there's other YouTube channels as well that I would also suggest. So Florian explained that I will not call myself an AI expert. So this means more than usual. If you feel I'm saying something really stupid or even just a little bit stupid, then please stop me. And in general, stop me anytime you have a question or you want to interrupt. No problem with that. Otherwise, I also, like Georg, I have a slide about what should be expecting from this talk. So this is going to be very high level. I have a few technical details that I would like to tell you about. But in general, the idea is that you get a rough idea about how deep learning works. There's so much going on, and there has been so many ideas. It's impossible to squeeze them in a little time. So it's really just to get a feeling. So it's particularly useful perhaps for people that do not know yet how these things work. Otherwise, I also want to touch some of the trends of research and industry. Then also we can talk a little bit about the problems that machine learning has, also maybe for society, not just the technical ones. And also I would be happy if I also have time and can talk about the maybe future that we will have. So every talk about AI or deep learning, I should say, starts with something like this. So out of my sources, I had maybe 4 or 5 copies of the same idea to show you. So just to make sure that we have the right terminology. So as a part of machine learning.
Just
yes, please
comment. I feel like intelligence is more like bigger field itself, in the sense of not only a term. Like there was the entire research before, let's say, machine learning existed. It was already called artificial intelligence. No.
Yeah. So it's now fine. Then the
No.
Yeah, I agree absolutely. So, but I want to ask you. Because it's a good experiment, a good, I think, good thing to think about a few minutes is to ask ourselves the question: what is intelligence, really? So, what do you say, Florian? What is intelligence?
Call me off guard.
Yes, that was the point.
That was the point of it. That was the point. Okay. Well, I mean, you can certainly name factors of intelligence, which is reasoning, first and foremost, I would say. Being able to explain observations, abstract is probably one. Abstraction, planning, I think, is an important one. To be able to plan to the future and be able to, sort of explain, not just do something, but explain why and how you're doing it, and be able to reason about it. So, is it reasonable what I'm doing? What are the limits? And things like that. But I'm not giving a definition of it. I'm just.
That's great. You touched already one important point, and that is a typical thing that us humans do when we are not, let's say, very knowledgeable in one topic. We tend to simplify it really a lot, and so it's typical that maybe you said already, oh, this guy is very intelligent. This guy is more intelligent than the other guys, and this already tells you if you can do that. It means that for you, intelligence is one-dimensional. So you can give a number to it. So you can say this number is bigger than the other. But if you think about it really just very little, you will see that it's not possible to do that because there's many facets to intelligence, as Florian was saying. So people in this field, they do have a kind of agreed more or less on one way of describing intelligence. But the general one, not yet, maybe in AI, would be the ability to process information which will inform future decision-making abilities. It's a very general term that maybe covers most of what you said, Florian. Otherwise, in the context of AI, of course, is the capability of a machine to perform tasks that would require intelligence if done by humans. So that's another way of thinking about it. Okay, let's say, well, okay, we have some idea about intelligence. What about machine learning? Florian, what about machine learning?
Machine learning is a little bit easier, I think, because I would say it is about finding out patterns in data by observing data that were maybe even not known before, and then abstracting from the observed data these patterns to apply them to new data and see before.
Okay, I propose this one that also I find more or less everywhere I've looked. It's a little bit broader, I would say. So machine learning, the science which studies how to make machines make predictions or take decisions based on data without being explicitly programmed to perform specific tasks. Just like I said, yeah, I think it's a good one. I even have some slide that explains it. So this will be what humans did for a really long time, more or less. It's basically we have some data. We come up with features or rules on how to make decisions or interpret the data. And then basically we put it into some program by hand. And then the programmer will basically do the, for example, classification or signal processing that we want. So in the real different paradigm would be the one you see on the right, where you basically actually start having your data and you have some task, some question that you have about the data, some goal. And then basically the machine learning takes all of that and spits out a black box that inside contains obviously some features extraction, some modeling, but not explicitly. So we cannot open the black box and see, okay, that's how the machine learning did it. And yet then you feed in the data and it seems to work. And of course, so we are very angry at it. And we say, oh, that's really bad because if this was really better than humans, then it should be able to explain itself and explain how it works. And yet we don't see that as humans, we are completely incapable of doing that. So you can imagine, oh yes, I think I used this and that feature to decide, but you don't know what's going on in your brain. We don't, not just you, also, I don't know. So we have absolutely no idea of physically really what's going on in our brain. So we just are guessing what the model could have been. And then we try to program it. And results show that maybe that's not the best way to do it. So learning from data in an automatic way seems to be an extremely powerful method. And the main reason is that it's scalable. So it means that you now put much more computational power, right, that we can actually acquire. And let's say we can solve the energy problem, then you can have something that is immensely functional. And instead, if you go for the programming, we are limited by our puny brains and our time frames and our energies. And this is the cool thing, the scalability, yeah, that you can make it really as big as you want.
It's also how kids learn.
I'm sorry? Yeah.
It's also how kids learn. The explainability bit is learning.
It's more complicated, I would say. So human learning is actually a complicated thing. So there's, but let me go to this when I have one slide. But I think the current consensus is that it's several mechanisms happening all at once. I want to go one more time about the idea why is learning features automatically so powerful. Again, the problem of ourselves as humans, we try to think about features. And just to make clear, what is features? Features is, for example, that let's say I want to do computer vision. I want to make a robot, and I want to make the robot able to navigate in this room. So I need for the robot to understand the geometries, right? So I could come up and say, well, there's only a camera seeing this picture here. So I need, for example, to identify lines, and then maybe I have to identify colors and so on, right? So I can come up with such ideas, and you can try to code everything. So for example, here you can see some example where they find lines and edges in pictures, or they find eyes and noses and ears if you want to do some kind of face recognition, right? Or even facial structure. But the problem is that these methods are highly brittle, meaning that if you change the data just a little bit, things that you have not considered while programming it, it will break completely. So it's a typical thing that humans come up with some smart algorithm, and it basically only works with a specific data set in a laboratory so that some person can get a PhD. And then you actually want to use it in reality, and it breaks immediately, right? So so you have that is brittle. You have problems that is not scalable, meaning that again, if you want to learn lots of features, it costs too much effort for humans. High dimensional data becomes untreatable. So basically our own limitations of our brains become the limitations of the software. That's why it's bad. Yeah. And robustness, I said already, just a general, something that I say, if you can scale it at some point, it will be better. So, and then the generalization as well. Okay, so we touched that. Deep learning, I'm haven't this set yet. This is really easy. I don't have even a slide about it. It's basically if you now have a neural network and it's slightly complicated, so meaning that it has at least one hidden layer, as we say, then it becomes deep learning. Okay, so my suggestion would be probably to say, in the usual term, it would be machine learning, maybe what you want to use as the more general term, and then go from that. Another slide that you find in almost every, say, older presentation will be something like this, where classically you had this distinction into supervised learning, unsupervised learning, and reinforcement learning. The reality, though, is that today probably is not so great to make these distinctions because there's lots of techniques that use mixtures. So, for example, the latest large language models, they use really basically, they have a supervised learning going on, meaning that there is a lot of data which has been labeled. Then there's a lot of course, also unsupervised learning, meaning that the AI takes now a bunch of data that nobody tells the AI what it is and learns anyway from it. And then there's also a little bit of reinforcement learning from the last steps in the post-processing when they want to fine-tune it, for example. But just to go a little deeper into these details, what would be reinforcement learning? And this is a kind of what people think about when we think about human learning. So the reinforcement learning would be more or less that you act into the environment, and then you get some kind of feedback out of it. And now based on this feedback, you decide to act differently. So this will be basically my son touching the oven, it burns his finger, and then learns, okay, maybe I should not do that. So, and as you know, as humans, pain or negative experiences are very powerful in making you learn. I'm sure if you, I'm sorry if I ask you that, but if you try to remember something bad that happened in your life, that will have a very vivid memory and will have changed maybe even your behavior significantly, much more than positive feedback. But anyway, so this is kind of the scheme. And if you look it up and see, okay, how people think that humans learn, it's actually a multitude of mechanisms, and reinforcement learning is just one of them. The way the brain also learns is different than what we do with our computers, because what happens in the brain is that as the neurons fire, they basically get that particular connection more, let's say, easy, so that that particular pathways will be more preferred or will have a better transmit, let's say. And this is also why by repeating something, you basically store it, so to say, because you keep reusing the same pathways more and more. And in this way, they basically become more efficient and the dominating ones. That's at least the typical explanation for that. Yes, please.
Can we do the same thing to the machine?
Yes.
As you said about, let's say, emotional or negative experiences.
Yes.
To give the machine negative experience, like
Yes.
you go this path.
Yes. So reinforcement learning is also used. I think the main reason why it's not the favorite one is that it's slow, because it's sequential. You basically have to have the machine do something, and then you have to give some feedback to it, and then you can continue.
Yes, but as the time passes, it will become better and better.
Yes. I do have a slide about that, and that would be the very important question: why are current AI models so-called one-shot models, meaning that they are basically fixed machines, and now you use it, and there's no learning, as we call it, online learning, meaning that it does not learn from experience in any way. So, and the reason why that happens, if you want, I can just quickly jump to that. Why not? I have to remember how the pictures look like for online learning. So this is the hardware. So this is where ChatGPT would help me say, where is the slide about the online learning?
It's okay. It's
Otherwise, please just keep in mind. I will touch it.
yeah.
So there's really good reasons why they don't do that. Although it sounds like a great idea, but there's several reasons for that. Let me get this out again. There we go. Right, I just want to touch relatively quickly on the different methods, just to get you an idea. So the other one would be unsupervised learning, where the AI gets a bunch of data and we don't label it. So we don't say anything about it. So it cannot learn, for example, okay, these are oranges and these are apples and these are carrots. And in this way, when I show another picture, then it can distinguish. In this way, with unsupervised learning, the AI basically finds clusters of whatever features it finds on its own, right? And this could be useful to make sense of data, for example, that otherwise you don't know how it works. A good example would be from Florian's slides, like the suggestions they make on music or on what to buy next. More or less works like this, meaning that they just put buyers or listeners into categories. And if now they find that you belong to this category, now you can, they know what you will like. So very simply, right? So, and of course, humans like to believe that they are special, but they are not. And it works really well there. So meaning that we are much more predictable than what we typically would like to admit, right?
I have a question.
Yes.
So basically, you don't tell the computer which pattern it is. The code is trying to look for the patterns themselves.
Yes.
So do the people need to give some feedback to the classification?
Yeah.
So make sure the computer knows.
Yes.
It
depends on the purpose why you're doing it, right? So more or less the main idea is that the computer learns to compute features and then looks for those features that distinguish the best the categories.
To tell, excuse me, do you have to tell the algorithm how many clusters?
It depends. So you can do both. So there's algorithms where you tell how many categories, and the algorithm finds the best way to place the data points into, segment them, into these categories, into a certain number of categories, or you can also leave the number of categories free.
So if you don't tell it, how do you know if it has been categorized?
Yeah, it depends all on because at some point there's always some kind of a loss function that basically tells the algorithm how well it's performing. And in some way, you have to then see that there is you have to make a trade-off between having many categories and how well they are separated. So you have to put a kind of a penalty for having more categories. Otherwise, you get the trivial solution that you have one category per unit. So therefore, it must be like a penalty. This is a soft thing that we decide as humans what is for us better, depending on what your goals are. Yes.
So from what I remember, unsupervised learning is usually mostly for descriptive tasks. So like, what if I give you the taste of music, and like in which category you fall into, based on the fact that separate music samples will have different, I don't know, characteristic features like BPM or peaks, like, or presence of bass or low. So that's really left. You don't tie anything to the algorithm, to the learning algorithm, so the model itself, and it will try to separate your music dataset based on some sort of numerical features.
Mm-hmm.
Also, not numerical.
Yeah. So, and of course, you always have the possibility to either give the machine learning algorithm the raw data as it is, without, for example, extracting anything. Like, let's say, if it's music, you just give the WAV file and let it do. Or you can already decide to extract some features, for example, beats per minute and loudness and some other features, and you give those. So, and now, as usual, The statement should be that if you have enough data, the machine learning is able to learn regardless of any other input. But the amount of data that would be necessary is much more compared to if you already give the right features. The problem is as soon as you give the features, you're already, let's say, giving a certain bias to the interpretation of the data that maybe was not the proper one. Okay, and instead the supervised learning would be then that you actually have your data, your input, but you also have a real clear idea about what the output should be. And now you give basically these data sets as pairs, meaning, so for this input, I expect you to give me this. For this other input, I expect you to give that. And this is then how the machine learning will learn, trying to be sure that from the certain data comes out the correct output. So, and then there's typically a distinction between classification problems where you have categories. That could be, for example, for computer vision, let's say you want to distinguish cats, dogs, and mice, I don't know. And other problems that usually we say regression, if you then expect some real number coming out of the as an output. Okay, just to give you a very rough idea. So next I want to go into some history, really just one slide, I think, or so. And then I would like to ask a question also coming from Florian's slides and others. So why now? So why are we experiencing such a hype in these years? Because I think it's a really interesting question to ask and to answer a little bit more precisely. So you will get the slides. So if you want, you can look it up as you want at a later time. In fact, the main statement is that machine learning or artificial intelligence in general is really old. And actually, some of the important algorithms were developed really decades ago, right? But we start seeing maybe, I don't know if with AlexNet maybe, the rise of a new generation of algorithms and incredible performances. So basically, it looked almost like we had very little success for a long time, and then suddenly now things are working.
So from what I remember, it was like the last decade, from 2010, AlphaNet, it was a competition. It was and outperformed by 30% all the others.
Yes.
So that's kind of the deep learning era. And so before it was machine learning, more models, which was mostly,
I think it's, so if you look at the history, it's complicated a bit. So there's also several periods. So somewhere here, there's the first winter, as people say, then there's a second winter. But also, it depends a lot if you look from the perspective of the United States or the globe, because it's a very different story as usual that you can tell if you only look at what's going on in America, in the United States. But I think it's more, I think it's less interesting to discuss in detail, okay, when exactly did it start and what was where. I think it's, if you don't mind, I'd like to bring the discussion into why now. And so this is the slide for why now coming from the MIT lecture. But if you don't mind, I would like to expand a bit on it. So basically, the statements are that the availability of data is in this time, in these years, particularly at a level that is what we need. I would also claim that there's a clear trend in the direction of open science. I will go into these details of all of them. There's some hardware improvements, so hardware capabilities that we didn't have. There's significant jumps in terms of algorithms, but also in software frameworks. There's a clear commercial interest. There's money flowing, basically. And there's also a lot of money being pumped into the system, which one should not forget. And actually, let me already tell you that it's, I think it's a really good idea to start thinking about hardware, algorithms, and software together. And actually, the new term that people use is compute. So actually, you will want compute and you will buy compute, and you don't care so much really how it's realized. So if it's on a GPU farm somewhere in the cloud, or you have it in your basement, it's not so important, and people talk about compute now as a metric as well. So let me go first of all in the direction of big data. So big data means, of course, that we have lots of data available for playing. So at this slide, where you can see some of the many data sets available for the different fields. So one of the most famous one is the one from NIST. So the institute, so the American Institute for Standard. Oh, I forgot the name. I always say NIST.
Standards and testing.
Standards and testing. Thank you. So they have this modified, where this is the famous one, where you see so many. I think I wrote it, 70,000 images, 28 by 28, where you see just the numbers, and then you can basically play with it easily to see that you can learn how to distinguish numbers. And AlexNet was basically destroying the competition in ImageNet, which is also a data set and also a competition, basically, where the idea is that you develop benchmarks. This is also a fundamental thing that is happening in this last decade, maybe, where more and more data sets are being put online and more challenges are being opened. So basically, you have the possibility to test your algorithm on some known data set and compare results with others. And this is essential compared to classical results in, let's say, communications, for example, where I could write a paper and derive a formula. And then basically, let's say I have optimized for SNR and my computation is, my derivation is correct. That's it. It's the optimum. I don't need benchmarks. I don't need, so I just need the proof, the mathematical proof, a few lines, and I'm done. And when you use machine learning and you do your own tests in your own lab, it would not be comparable with other tests, and therefore would make the research kind of useless. Therefore, it's so essential to have such data sets and also benchmarks or challenges or competitions to compare. And more people are putting these things online. So the question would be why to make it available then? Is of course that people do it because they also want to
Flex.
flex. Well, you get lots and lots of citations. So, and it's also a lot of work. So you have to get the data, clean it, make sure that it's correct, put it out, and then you basically have some paper as a reference, and then people will cite you. And of course, this is more and more also in Germany, for example, requirement when you get a grant. So you have to publish all your results. And I think it's really fair because if you get money for public funds, it's fair that you give back basically all the results. Right, and then of course it just generates a certain amount of mass moving.
I said the flex because what I remember when I was studying, like the fact that you have your own data set and then usually you're accompanied with your own model and you prove that your model is the best in the data set A, B, C. So that's why it gives a bit of recognition impact. Like when you are doing the state of the art, you can claim, I am the state of the art for this.
I have to be honest, I haven't seen it so that I could mention one thing where this happened. I would be though not too pessimistic because the community will basically stop using a certain data set if they feel that it's biased in some way, that it's not representative. So I would be less preoccupied about it. So meaning that I think that the data set will have to be fair and representative. Otherwise, the community will just stop.
That's I mean, it's good that you make it available publicly because other people can use the same data set and achieve similar performance, worse or better, and that will give you recognition because they are.
No, it's fine. I understood more like, okay, you choose your data so that your model looks better.
Yeah, but then if you don't, you do that, and then you don't publish the data, that's suspicious. But then if you publish the data as well.
Yes, but this is nowadays, it's kind of the norm to do. So just publishing an idea without some test on some existing data set or publicly available data set will probably be not published or will be will have a much less impact.
In fact, I would want to add just one more point to this. I think one reason that also really helped the creation of data is that nowadays everybody and their mom is carrying one of these, which is a great unit for generating data and making sure it's on the internet and social media publicly available, and people are sharing it very voluntarily. This has created a huge data volume that would have not been possible without the hardware and without the internet, of course. So
Yeah, and yet I come back to that because I have an interesting plot that you probably do not expect. So talking about challenges, well, the fact is that most challenges are already beaten. And so people are coming up with more difficult challenges. So for example, they have all kinds of PhD level questions on different fields in science, because the normal exams like bar exams and like state exams are basically already beaten. And so they go at the PhD level, basically, because yeah, the AIs are just too good. So you can actually look it up for whatever model, what the kind of exams have been passed. It's kind of crazy. So what I have here is, yes, exactly that. So the size of the data sets which have been used for the training for different models. These are all large language models, like ChatGPT, for example. And you can see this trend, which is kind of scary. There's no sign of slowing down, although they also computed how much text is in general available on publicly. And the current guess is by 2028, we will have trained on everything that has been written and think about it, it's absolutely nuts. Okay, so we have to get going and produce more.
But more here is that some companies are building generative tools to generate text to train their model on. So that's a terrifying recursive loop.
It's of course a dangerous thing to do, of course. Yes. But anyway, so these numbers, I also leave it in the slides for people that are interested to see more details. It's kind of scary. Okay, so the next thing I want to talk about is the trends to go into open science. So first of all, why open science is a good idea. I think I do not have to convince you. So by discussing, I actually said basically the same thing when I said that we should discuss as much as possible with each other and with the scientific community. You get faster innovation if you do that. So just bringing your idea on the table and having somebody else look at it, it's so useful from the interaction, you get a much better idea. So trust me, do it as much as you can. But also if you have open science, it builds trust and it builds safety, because there's more people immediately trying to misuse the thing, and you can develop systems to prevent misuse early, instead of thinking everything is fine and then you put it online and then half an hour later somebody found a way to completely break it. This happens anyway, but it's much worse if you have developed it for a long time without any feedback. And then, of course, it's great for reuse of research data. It's a pity to make an experiment very expensive and have only one thing run on it. And of course, it goes into the democratization of research and knowledge in general, so which is great. I think not so intuitive is the question, why do large companies do open science, right? And a little bit it's for the same reason. So they also want to have fast innovation, but somebody could think, well, why don't they want the innovation for themselves though? Because that sounds counterintuitive. And there's a really good reasons. And believe me, if a company does something, there's a good reason for it. It's not because they are, I mean, for sure, they're also nice people, but it's not because of that. The company has to make money. That's the system there. So they also want to do something very important, which is to generate de facto standards. So even though there is no standardization body, they want to make sure that the way they do it, or the way the data is interfaced, or whatever, is compatible to what they're doing. It makes it much easier than to reuse, for example, things that have been developed. You get a larger community. You also get a perfect way of getting people interested and to see talent for example. It's a really big thing here. If you make it easy for anybody in the world to get a computer, even not very powerful, and try stuff, and maybe get a good idea, then you can see this person and try to acquire him or her. So that's another reason. But the main reason, as usual, is money. And to understand why it's actually a better idea in terms of money, you have to understand the business models behind such large language models, especially, but AI in general. And the idea is that they make money by providing a software platform, by providing infrastructure, or by providing data. And almost never can they make money because they have the better algorithm that it's patented and secret. That's not the thing. And this is I would say, the main reason why we see that companies are happy to share ideas, because they then have the upper hand in that there's very few companies that can actually train such things at all. So there's no danger that somebody who knows where just does it in his or her apartment, right? And even though, if the algorithm is public, they can also implement it, and then they can sell the service. So the idea would be that there's no need of patenting, and also it would be very difficult to make a patent and protect it in any way. So the business model is separate from this having the smart idea, and therefore it's great that the smart ideas are shared in an academic way, open and with papers. They can still take everything and implement it and still make a lot of money. And that's actually not a bad thing if you think about it. So if you think about other kind of technologies and patenting in those technologies, then it is much more so that you really would like to develop your ideas hidden from the world and get to the patent and only then start talking about it. But in this way, innovation is not as fast. So I think that's another reason why we see such a huge hype and progress, because there's so much communication and open science. Let's go briefly into the hardware. Maybe I finish this slide and the break. Yes, please.
About this software, they are owned by companies from the United States. So there is a war now somewhere between the Chinese, I guess, that are trying to end Europe, that is lost in between, because if they have all this power, how is it outside the US?
So the idea is that you're right. So these are mostly, if not all, American companies. So they basically set up their business models to give such services. And so they are happy if you learn how to use PyTorch, because then you are happy to be on my platform and you pay me for that. And this is basically what we see as being a really available. There's a whole bunch of open source stuff that you can also use. But at one point you will need compute, for example. And this is where you probably will have to go into one of the companies, like Amazon, for example, and get your algorithm running on those servers. Because it takes a huge amount of investment to get something like this going. And so this is kind of the bet that they make, and they are winning it in the sense that if they have the platform ready, and for you it's very easy to start by just simply buying some resources, pay for those resources to get the service running. They can get you running with your new business idea very quickly, and they earn money out of it. So
that was the same idea of cloud computing in general.
Yes.
For cloud services.
Yes.
Like Gmail or like Google Photos, or I don't know, other services, Outlook that we use, or Word. They all offer computing remote service that you then get into it and start to get out.
Yeah. So of course, Google has also the bigger thing is also getting data. So that's also why they are happy to host you, so that they can learn out of your data. Yes, but the main idea would be basically, we see this also in retail. If you think about Amazon or Alibaba, AliExpress and the like. So what they have all become is a platform. So basically, it's a platform where people go, and there basically anybody can sell, and they always get a cut out of that. So this getting the platform is, or like Android, for example, why it's developed, it's exactly the same reason, or why iOS, again, it's the platform on which people sell, and then Apple gets 30% for everything you buy on the Apple ecosystem. I mean, in the App Store, it's called. Let me touch a bit on the hardware. Because also I think it's a very nice and interesting thing to realize why we see this hype. And I think it's such a fundamental thing to see that if you want to get things running faster, let's say, there's really two strategies. The first one is scale up. This is the classical that we probably all know from home. Basically, I want to do gaming, my GPU is too slow, I have to upgrade my GPU. Okay. The problem with scaling up is that there's a physical limit to how quick a processor can get. So this is really a physical limitation of the silicon technology, and there's not much that you can do about it. The main reason is that it depends on time, and time is really limited. You cannot make more time, unfortunately. So therefore, the better strategy that also nature, of course, has discovered, that's how our brains also came better, let's say, is the scaling out. So you use now space. So what you do is now you don't have just one CPU, you have 10,000 CPUs. So you just have more space to do your computation, but it requires that what you're running can be computed in parallel. Otherwise, it doesn't work. So this is another key idea, and that is that machine learning can be really great, but as long as you make something that is sequential, you're dead. Because it cannot scale. Instead, if you make something that works in parallel, now you can scale it as much as you want, or as much as you can, and you will get really a beast. So scaling out is the key. And this, I believe it's one of the main reasons why we have such great tools. It's because they have been developed for parallel computing. So this is the current plot for how much compute. In this case, it's computed in flops. So you can see the deep learning era, approximately 2010, 2012, I believe, when it starts going up, and it's currently going up with 0.61 orders of magnitude per year, which is like 4.1 times per year increase. Yeah, so I don't know. I'm excited to see it. That's great. Although there are costs for it, but we'll talk about it maybe later. So let's talk about algorithms and software. Right, software framework. So we've touched already a little bit about it. So here's just a few names. There's TensorFlow. There's PyTorch. That would be basically Meta. There's an Apache solution. Now it's owned or supported by Amazon. So, and there's a lot of things buying other things, right? So as you can see, but all the big players have some kind of software framework, and there's a lot of sharing compute discussion platforms. Bigger ones would be Kaggle, Hugging Face, maybe you've heard of it. So GitHub is basically also such a thing, which is now Microsoft owned. Google Colab, and it's very difficult to make distinctions because they more and more offer more services. So for example, Hugging Face, you can share your data, but you can also do computations on it, and you can also buy and sell. You can share, let's say, more general models. So it gets complicated. And there have been, for sure, a breakthrough in algorithms. So the advent of transformers, I talk about it later, just to name one. And they are currently guessing that we have about 3 times training efficiency gain per year. So meaning that the same data set gives you the same result as before if it was 3 times as much, right? which is also great because training is very, very expensive. Okay, this is the algorithmic process efficiency. So 3 times efficiency improvement. I basically already said that. So let's go into these last 2 points, then maybe we can make the coffee break. Yep. So let's talk about the commercial interest, which again, it sounds like something bad, but to be honest, if us humans don't see some money flowing, we will not work, so many of us, on the same thing. That's just a fact. So it's either basically something said like some war, or it's money, I would say, right? So maybe it's better that it's money. Hopefully we'll never get into the other one. But let's talk about a second about the AI economy. This is an extract from the report from Stanford. And the main statement is that the investment in AI is skyrocketing. Yeah, there are some numbers here, but just a huge number, so huge that you lose almost a feeling for it. And it's basically 2 players only. It's the US and China. And then maybe we can talk about who is third, but there's a big gap in everything, basically, in amount of PhDs being generated, in research papers, in models, in businesses, in investment. It's basically on all the numbers. And right, and let's talk in just a second about the cost. This is the amortized hardware and energy cost for so-called frontier AI models. So basically the cutting edge, state of the art. You can see how it's going up. And so it means that these investments are kind of necessary to continue progress, because yes, you can get more efficiency in different ways, but it's really clear the larger the better. So, and we're not there yet where we can say it's large enough. Let's tone it down. Let's talk a second about funding from different directions. You should not forget that a lot of funding for AI research has been actually pumped by the DoD, by the Department of Defense in the States. Lots and lots of money. And now they are planning 4.3 billions, you can see, which is actually not a big number if you compare it to what else they're investing here. But it's interesting maybe to ask the question, what is the strategic relevance? So why is the military so interested in AI? And so you have, of course, that you can gain much better situational awareness and intelligence. So for example, already today, governments with their military parts are scanning the internet. And for example, we have the war in Ukraine. There is intelligence looking at whatever social media to look for intelligence that is relevant for military action. Because everybody has a phone, everybody's posting stuff. And now you can basically correlate all this amount of data. And now suddenly you can localize, for example, a particular weapon of the enemy, at least roughly, and do stuff about it. So it becomes more and more important. Then you have, of course, autonomous systems, as you can imagine. And I'm sure you know, cybersecurity is a huge thing, both as active, so if you want to be aggressive with it, or if you have to defend yourself, huge thing. And also some gains in logistics, so that's clear. So maybe this I skip. Yeah, okay, so I think it's a good point to stop for a coffee break. Thanks a lot for listening. And let me tell you a little bit about some technical details, because I think they are still interesting to discuss, although at a very high level. I just go through, first of all, how the basic unit of a neural network works. This is the so-called perceptron or a neuron. You can also say neuron. Then we talk about if you put it into a network and how that behaves. And then I want to talk about recurrent neural networks, so that I can at some point arrive at self-attention and transformers, which is the core of large language models, and such a clever idea, the whole thing. So the neuron, this is really old stuff, and it's a little bit biologically inspired, although not exactly. And the idea is that the single neuron does the following, has as many inputs as you want. It basically collects all the inputs. It adds a bias. It adds a bias.
Sure. Can you?
Somebody has a microphone? Okay, it's done. So it adds a bias. And then this is just one number. So this one number goes into a nonlinearity. And the output of this nonlinearity goes to the next. So meaning that these guys coming in, these blue ones, probably came from other neurons or are the input. Okay, and the interesting thing now, right, is to discuss this part here, the nonlinearity. This is so essential. And so I teach also courses in basic circuit design or circuits, basic circuits. And there's a nice theorem that we have there. So this is a very complicated network of linear components. So you have capacitors, you have inductors, you have resistors, you have sources here maybe, but all these are linear. And this theorem tells you that no matter how complicated this thing on the left is, this is your load, you can basically replace the whole thing with just this every single time, no matter how complicated it is. This is called the Thevenin equivalent. And you just have to find out what is the correct voltage here and what is the correct impedance here, so like a resistor, let's say, and you're done. So the whole behavior of what happens here is exactly what happens here, exactly. So, and this is so funny because in my lecture, I tell it like it's a great thing. Like, look, guys, you can now have something really complicated. We can simplify it and then we can continue with our discussion because it's equivalent. So, but if you think about it, it means any complexity here on the left is always guaranteed to be equal to the simplest linear circuit that you can imagine. And now suddenly it's a horrible thing. It means you can spend as much complexity as you want here. You don't gain in any way expressiveness. So you basically, the behavior that you will have would be the simplest possible, no matter how much complexity you have. So now you have to turn this idea on its head. And the idea would be, now actually we want something, we want this black box to be very, very clever, to have a very complex behavior, which means I cannot make it with linear components. I cannot, because linear components, no matter how you make them connected to each other, they will always just equate the simplest thing. So this kind of explains why you need to introduce nonlinearities. Something that engineers have dreaded forever, basically, because as soon as you have nonlinearities, you cannot write it on the paper and understand it clearly. So I don't know, in all my life as an engineer has been how to linearize, how to use linear algebra. And now I learn it sucks. Linear stuff sucks because it's whatever you do with it, it's too simple. That's it. That's the main thing. Linear things, which I thought are great, are not so great. So here's a very simple example. Here's a classification thing. So you have two possible variables. I don't know, like a height and weight of something. I don't know. And you have your data. This is labeled. So you know this guy is red, this guy is green. And now you want your behavior of your network to tell you if I give a new point, is it green or red, right? So if you have a linear stuff, linear network, no matter how complicated, at the end, it's going to be one line somewhere. That's it. No matter what you do, always just one line. Obviously, one line doesn't work. If I have one line and I can say, let's say green and red, it doesn't work. So with this data, I need such a complicated boundary, and I cannot learn it, I cannot represent it, I cannot express it with a linear network. I need nonlinearities. So this is the reason why nonlinearities are the key.
But this is not a linear function, but like the one on the right, it's not.
This is nonlinear.
Exactly.
Right.
That's not a function.
It is a function, why not? It's a function that takes x1 and x2 and spits out the category. Yeah.
In that sense, yes.
Yeah. So in that sense, it's a function, yes. Okay. Okay, so, and this is this place where we have basically the so-called activation function, which is where you introduce the nonlinearities or the nonlinearity. And the funny thing is that scientists have used several different ones. There's also a lot of things to be discussed here. So here's some famous one, the sigmoids, the hyperbolic tangent, but the one which has the most famous, let's say, or most used today, I would claim would be the ReLU, the rectified linear unit, or the leaky ReLU, or some small variation. But the funny thing is that they also found out that, yes, one maybe works better, but actually it almost doesn't matter which one you use, as long as you have enough neurons, it will work. Okay, so keep that in mind a second, because I come back to it. No problem. All right, so let's go now into connecting such neurons. So let's go into deep learning, basically. And the idea is that you will have some layers put like this. You can go ahead and connect everything to everything, basically, right? So this will be just one layer. As soon as you have a hidden layer, you can talk about deep learning. And if you have many layers, then you can show it like this. And every layer will be connected fully with the next, for example. And that's how you build a network. And then you can decide on things like how many neurons shall I have here in each layer, and how many layers shall I have, for example. So there's many things that you have to decide. So, but here I want to really, yes.
Just, I noticed, like in my previous experience, for training a network takes a lot of iteration.
Yes.
So is there any thumb rule?
Yes.
To choose?
So this is a really open research field. There's some people actually trying to derive scaling laws, they call it. So to really say, if I have so much data, what kind of, so there's the question about how to use the data. So we'll talk about it in a few slides. Then there's the question about how should I decide the dimensions of my network, and how many iterations, so how many epochs shall I have. So there's they're trying to get some laws for it, but I would claim that more or less today it's still a lot of trial and error and learning from experience, meaning that humans still realize, I should use this and that, and then they see the behavior, and then they can think about why is it like this and how can we make better and make changes. So it's definitely, we are far, far away from another neural network where you give the problem and it spits out what would be the perfect neural network to solve it. Yeah, please.
Yes, you brought in the analogy of circuit analysis, right? In fact, now they mentioned there exists like a chaotic circuit which produces like chaotic behavior, right? And it has like some diode component, which it's like an inverse sigmoid essentially, right? So is a neural network as a chaotic system, or does it exhibit chaotic behavior?
No, I would say no. It's not chaotic system, and it's also a deterministic system in the sense that there is no there is no noise and there is no randomness in it unless you find a way to feed it into the system. So in this case, diffusion models would be a good example, where you basically, so for any generative AI, for example, for images today that works well, I would claim works with diffusion as a diffusion model. And the way it works is that you basically start with noise, some Gaussian noise usually, and then out of the noise, you ask the AI basically to generate your image. And the way it works is that the network is trained to remove the noise from the image, so to spit out what was the noise on this image. And then you're misusing it, because if you now just only give noise, suddenly the AI will see something in it, which was not there, because it's just noise. And suddenly maybe a speckle and some black pixels suddenly become, let's say, a button of my shirt, and some other pixels determine the color of my shirt, if I have to make myself, for example, right? But it's a deterministic machine. So if you give exactly the same noise to this neural network, it spits out exactly the same image. Okay. Okay. What I want to tell you now is another concept that I believe to be really powerful and interesting, and that's also something that we see in the circuits, and that is that suddenly the behavior of the single component is not so important and not that important compared to the network. So, and let me give you two examples that I like very much. One is the operational amplifier. If you know some circuits, you will find yourself in this discussion, because the operational amplifier is basically an amplifier that takes the delta voltage here and spits out the same times a very big number. Now, the funny thing is that we don't need to actually know exactly what this big number is. As long as it's big, let's say 10,000, 100,000, then you can make an architecture, for example, like that, and then the behavior will be always the same. So what I mean is that if your amplifier here has 10,000 as a gain, it behaves the whole thing the same as if it's 50,000 or 100,000. So what I mean is that the behavior is not decided by the single component anymore, but it's decided by the architecture. It's a very powerful thing to understand. And I have another example for that. I like even more. Let's say I have now many, many components, right? So these are random variables. Each random variable has a certain PDF, certain probability density function. Now I add them all together and I get a new random variable. So now what will be the PDF of the sum of many, many, many random variables? Brilliant.
Gaussian
A big Gaussian. So meaning that it doesn't matter how these PDFs look like. They can be anything. But if you have many of them and you sum them up, you sum up the variables that are distributed as whatever, what you get is Gaussian every single time. Again, it's the architecture that decides the behavior that is Gaussian and not the individual parts. So these things we call emergent behavior, emergent properties. And it's really, I think, a super interesting research field. It's basically related to the emergence of complexity, where you can see that you have individual components and they have a certain behavior, but when they are together, the whole thing macroscopically has a completely different behavior. And the behavior, many times, is not decided by what happens in the small one, but it's the architecture, so the way they are connected. So, and this is a good example here, for example, the school of fish. So if you have many, many fish and they're small guys and they stay together, if you see and there's a predator coming, like a shark, I don't know, some bigger fish eating other fish, what happens is they behave almost like one machine and they start having really complicated but super coherent behavior, although the individual rule of a single fish is super simple. So this means this complexity of behavior comes from the architecture and not from the single component. Yeah.
So complexity eventually leads to simplicity.
To?
Simplicity, if you sum up.
Not necessarily. So if you have many, many, many things, you can have a new behavior. It could be also simple behavior, but it could also be complex. Yes?
Yes.
So, I mean, we experience every day with our brains. So the single neuron is really, really simple. I mean, we can really measure and know pretty well what happens with it. And yet, when you put it together, sure, some billions and with trillions of connections, but the overall, we have no idea how to really treat and say how it works. So, and it's the architecture that somehow gives the final behavior, and knowing very well how the small one works doesn't help that much. So, very powerful, in my opinion, concept. And I also wanted to depending on which level of size we look at things behave very differently, and they can be completely even separately from each other being described. Yeah, so I'm talking about, for example, quantum physics. Somehow we cannot derive from quantum physics the macroscopic behavior. And yet, everything is made by fundamental particles. And we just don't understand very well how we go from this level to this level. They are connected somehow, and we are completely clueless in starting from this and derive the other one. So this is also why it's so difficult to derive how a neural network will work. We just basically are like really primitive monkeys. Basically, we're just putting it together and then looking, oh, it works, great. But we cannot design it. So at the moment, we're completely clueless on how to design from the beginning and say it will work like this. So for example, we are completely incapable of saying, if I put a factor 10 more neurons, it will have this ability. No idea. We're guessing, we're looking at the curves, but we basically don't know. So it's super interesting research field, super in its infancy. So
but it has a statistic phenomenon, right?
No, I think the emergence of new behavior that is being observed was a surprise. And you could not have predicted it because it's not just a linear expansion. So it's really clear to see that as you increase the size of a large language model, certain abilities appear suddenly, and you are not able to predict them. Actually, I'm super excited that it's this way because it means that maybe by scaling factor 10 more, maybe then it starts working really at a different quality. That makes us happy, and we cannot predict it. So what I mean is that making the large language model double bigger doesn't tell you anything about the capabilities that it will have. Yeah. So we really had to try it and then really see, wow, now it does things that sound like magic. And it's not just a factor so many compared to the previous models. So going into the just what is my deadline? What time?
So you should finish in 3 minutes. But
in 3 minutes.
We started a quarter of an hour later, so I would say we can take around 20
minutes.
So.
Okay, let me start the timer so that I know what's going on. Okay, so we have this network, but the network is useless unless you find a way to train it. So the idea is that, okay, we have this network. If you put in the right weights, these connections and the right architecture, it's magic. But who gives us the weights? Nobody. So nature has, of course, had the luxury of having millions and millions of years of trial and error, basically, to do stuff. We want to be a little faster. So the training is an essential part of doing this kind of stuff. It's useless to know this has the potential of doing great things, but nobody tells you the weights. So this means that we have to go into this discussion, and the whole thing works with the defining a loss. And the loss, as you can see here, what it does is very simply, it does the following, that so we are in the supervised learning paradigm here. So what we do is that we have a certain input of which we know what the output should be. And now we basically feed in the input into the network, and we get this F is the prediction of the network, and we compare it. So meaning that this is the output that we should get, and this is the output that we get. And then we see how well it matches. And this is a signal for the network to know did it do well or not. Okay? So there's a lot of discussions here, maybe, but the main idea, I would say, works with the so-called gradient descent. So let's now do an example. Let's say we have a super easy network. We have only two weights, W0 and W1. And this surface that you see is the loss function for all the points. So all the points here in this parameter space, meaning that given a certain data set, you can take the W0 and W1 at a certain point, compute all these losses, make an average out of it, and this is this height. So which means that if we were in this minimum, it would be best because then we are closest to so the prediction is closest to the actual thing. So, but maybe we start here and we have to find a way to get to the bottom part. So, and this is done with, actually this is a relatively well-known problem in math. There's lots and lots of ways to do it, efficient ways, but the real key was to find a very efficient way and a way that is that can be parallelized. This is the key thing, because then we can train fast. And so let me do this, as we have not that much time, let me skip to this, which more or less is the trick that we use, meaning that if you now want to go to the minimum, sorry, go back. What you really want to do at every point is to basically look around in this place and see where am I going down the fastest. So how can I improve the fastest? And you have to find this direction. And this direction happens to be the negative, or so the negation of the gradient. So the gradient tells you in which direction am I going up. So you want to go the opposite direction, right? So more or less it's like this. And computing the gradient would be very, very expensive if we didn't have something that is mathematically sound, which is the chain rule, meaning that so the gradient is nothing else but the first derivative. And the first derivative of something which is a function of something else, you can expand it with the chain rule. And what happens is that once you are letting your data flow in the forward direction in the network, meaning that you want to compute the predictions, already you can store the information what was the derivative there. And so once you're done, now you take the results and you go back with your computations, and you can compute at the end when you're done, you can compute how you should change your weights at every step, basically. So again, I would like to be a little bit more time to explain it. The key idea is that it's just a very efficient way to compute the gradient. So, and it's a key thing because it means that we can train with more data because it doesn't take that much time or energy to do it, because we have a fast way to do it and it's parallelizable. Another issue that is very important in such discussions is the fitting, meaning that you can see here some data that you expect your neural network to see, or to predict. And what happens is that you can train and train and train, and at some point you will be actually really, really close to making a prediction, which is really accurate. But what happens is that data typically is not perfectly clean, meaning that the data should be just a representative of something, because at the end, you don't want to use it on the data that you already have. You want to use it for new data. So you don't want to have that a large language model gets a question that is already in the training data set, and it spits out exactly what it should be, because that's useless, we know already. We want to ask a new question, and we want a sensible answer. So, and the problem here is that obviously if you're in this region is not good, because it hasn't learned that much. But here it has learned too much, meaning it has learned to fit the data that you've given, and therefore it's less generalizable to a new question. So this we call overfitting, and it's something bad. You don't want it. There's several ways how you can avoid it. Let me show you just this one, which is basically showing the loss that you get with the training data. So as you can see, as you're training, so you're improving your weights, your loss becomes smaller and smaller. And you can go basically to almost zero. However, now you have another part of the data which you are not using for the training, and it's always like new data for your network. And at every step, you try, okay, what about if I give you this data? What do you tell me? And you can see if it's working well or not. So you can see that the loss is higher for the testing because the network did not know it, right? But interestingly, at some point, so it keeps going down. At some point, though, with new data, it's starting to get worse. This is the overfitting. So basically, the network has learned to fit the training data, but when you get new data, it's lost because it's not in the data set. So, and obviously, you want to stop at the minimum of this curve, and that's one way they do it. They basically keep training until they see that it starts getting worse with new data, and that's how they know they can stop. Okay, this way I can skip. So let's go very quickly into the Next problem, because all that I showed you is great for data that has a very clear dimensionality. So like an image, for example, it's great there because you know your image is 128 square. That's it, always. But lots and lots of data useful for humans is sequential in nature, like a text. So a text is never of a certain size. So if you write text, it's going to be shorter, longer, right? Or music, for example, it has a certain changing dimension. So we need something to treat this kind of data. And for this, we have the so-called recurrent neural networks that have basically this idea that here you feed your data at different times. So you can go on as much as you want. And the idea is that the neural network will have some kind of memory thing, meaning that you can send some state, they call it, into the new iteration. And in this way, the network can basically be as long as you want here. You just compute it multiple times. That's why typically it's written like you see here on the right, meaning that it's just the one thing within a recurrent loop. So you keep using it, and you can imagine, let's say you have a text that you want to do something on, and you just keep feeding a new word at every iteration. And when you're done, you maybe send a special token which says, okay, this is done, and then that's it. Now, what are the problems which were not really solvable for some time? The problem is that this kind of feeding forward makes it very difficult for the network to understand what should be forwarded further into the future. So basically, how long should the memory be, right? And so what happened was that the memory was always a little bit constrained. As you start writing a longer text, it basically forgets what happened earlier in the text. And then, of course, the answer doesn't make sense. So this was a really big problem. And also, I think, again, major problem is it was not so nicely parallelizable, which is a key thing, because if you can make it parallel, you can train with the super big guns, and now you can scale. And if you scale, you need the scale. Otherwise, you don't get these super abilities that we want, right? So scaling is essential. There were some other in-between solutions, which I'm going to skip. And the real killer was the idea of self-attention. So this was this very famous paper. I wrote it, 125,000 citations. Okay, Guten Tag. And they call it also, they didn't know that it was going to be so famous. They call it with a funny name, Attention is All You Need, which is now very famous, of course. And this is the following idea, which is actually at the end quite intuitive. And the idea is that, so you have a text, and what you want to do is to come up with such a matrix, which they call attention weighting matrix, which basically you should imagine, let's say I have a text with 5 words. And this basically tells you how each word is relevant to understand another word. Okay? And this is a matrix, meaning that, so of course, the word itself is very important. So that's why you have an identity matrix, basically. But then you see that, for example, the 5th word is relevant for the second. So they have to go together, right? Now, the matrix is not symmetric. It's not super easy to understand, but I'll give you an example. I hope it convinces you like it did for me. Alice noticed the beautiful painting. Now, the word beautiful is very important as context for the painting. It changes completely how the painting should be understood, because it's a beautiful painting. But the adjective beautiful, for understanding beautiful, is not important to know painting. So this is not symmetric. There is correlation for sure, but it's not symmetric. So, and this thing is basically the key thing, because once it's called self-attention, because it's the attention to itself, so the input with itself, it basically, like humans definitely do, they put information pieces together. So they basically, let's say for an image, they make immediately connections and say, okay, this is a frame of a window. So let's say I have pixels. All the pixels of the frame go together because together they are the frame of the window, right? So if you're looking at some animal and you recognize some pixels, again, we don't see the pixels, but cope with me. And I say, okay, this is the tail. And now the tail is relevant because together with the ears, I can see it's a cat. Yeah. So humans do it in our brains. We do it automatically. Our brains gives us to our cortex the already fine-tuned information already put together and diluted. No, sorry, not diluted. And concentrated, so that only what is relevant is given to us. I'll just give you an example. You sleep and there's a clock ticking. Your brain filters this information and you don't even hear it anymore, right? Or let's say smell. You go into a room, it doesn't smell so nice, or maybe it smells good. Few minutes and then you don't smell it anymore. Why? Because it has become not relevant anymore. Your brain suppresses it. It's the same idea. So the idea is we have to find what goes together, and this can be fed really far in the future so that the network will remember stuff really in the past. So this is the complicated way how they do it, but this is the main idea. And here's the key thing. The key thing is that the input is never seen separately. So each word, that makes no sense. The words are put together and the algorithm knows, okay, this word, to understand this word, I need this, this, and that. And this could be really far in the past. And the key thing that they found is that with this method, they can make it parallelizable. Again, big guns, scalability, you start getting emergent properties. Long dependencies, I already said. Okay. 5 minutes, perfect. So this was the key idea that led to having transformers. It's maybe one of the key features of a transformer, and led to such a great jumps in progress. So that today we have these beasts of large language models. So let me tell you a few information, a few graphs about it. So one thing is that they are becoming really huge. So this is the number of trainable parameters. I believe we are in the trillions even, isn't it? So this is giga, giga, tera, right? So this is millions, billions, the language is back for that, in trillions parameters, which is a crazy number if you think about it, right? This will be the current scores for different abilities. You can see, for example, reading comprehension, image recognition. So behind everyone, there is, of course, a test, a benchmark. And the current models have reached human level in many, many things. That's why I said that there's new challenges and benchmarks that are being developed. Here's another list. This is a very nice site that keeps track of all the results from benchmarks. So you can see all kinds of pieces of intelligence, right, that have already been cracked. This is this context window that I was talking about. So how much memory does it have? And this is huge because we have now reached the levels so that you can basically, for example, let's say that your AI, your large language model doesn't know Harry Potter. But now you have a question about Harry Potter. So before you have to have training which contained Harry Potter. But now I can give Harry Potter, which is crazy, as a prompt. So like in your ChatGPT, in the window, you copy all the books, I don't know how many, 10, I don't know, all the books, and 10? Seven. And then you ask a question about it. And the thing sucks it all up and answers based with that context because the window is so huge. Now think about the implications of that. It's crazy. Okay, this I can jump. This maybe I jumped as well. Therefore, let me go into maybe the negative side. You can see I'm excited. I'm that kind of scientist that others have to stop and say, wait, think if you should and not just if you can, right? I'm more the guy who was happy that we can. There's a whole bunch of problems, unfortunately. So of course here from Forbes, so the 15 biggest risks of artificial intelligence. I'm copying from Florian presentation. Yeah, you could spend hours talking about them. Some of them that for sure you know already, for example, bias and discrimination is a big one. If we now train poorly, now the AI will be biased, of course, right? And if we use the AI to make decisions, now the decisions will be based on data that we feel should not be representing what we believe in. You have, of course, dependence on AI. Maybe the future generations of engineers will know nothing because they don't need to. They have the AI that does everything. At some point, it's a problem, right? Job displacement, obviously. Many jobs will be obsolete and because they will be automated. This happened already, of course, yeah. But this is a different scale, right? Very different scale. AI arms race. That's also why militaries are looking for that, because there's also the understanding that if you have a very powerful machine, you have an advantage over other countries. Loss of human connection. I spent hours discussing with ChatGPT as I was preparing the presentation. Now I call the ChatGPT, I can call it my AI friend. The ChatGPT told me that I can do that. It's fine. So we are AI friends. So yeah, that's also a problem, right? A very big one, misinformation and manipulation. Florian, I'm going to show you your plot here. All right, let me get it. Here it is. Next. Yeah.
この短いビデオでは、現在の AI の能力を示すための別の力を紹介します。言語の自動翻訳が許可するもので非常に魅力。
Okay, so this is Florian speaking Japanese. Florian, would you mind repeating in Japanese?
There's two things you need to know about this. A, I don't speak a word of Japanese. And B, in case you don't, this is perfect Japanese, as my colleague that comes from Japan has certified. So it's crazy scary.
So this is something you can buy already. It's like 30 euros per month, right? You can put up a video of you talking. And do you give the text or the text is translated?
No, automatically. So I speak in German, in my case, or your language, and then you choose a target language from a long list of languages, and it does the translation, the mouse movement, everything.
But of course, you can change what you say. You can change your face. No, but understand that you can do anything. You can do anything. And this, of course, this is, of course, great and really, really troubling. Yes, very troubling. Okay, so my time is coming up. So if I find my pointer, let me then go into this slide. Just a few when I'm done.
Yeah.
Okay, it's really, so it's a huge field. I think it's very interesting. I want to talk a couple of seconds about future possibilities and then conclude. So the thing about predicting the future, this is a quote from Niels Bohr. Prediction is very difficult, especially about the future. I always like to cite it. So you could simplify with the two possible futures. The first one is the one I like. That the technology improves and there's going to be major impact in our productivity and employment, not necessarily bad. Of course, new technology, maybe new jobs as well. I myself really enjoyed using ChatGPT as a productivity tool. I'm actually super excited about the future. That would be better, and I will definitely use some more. There's lots of problems though still, like the problem of the fact that the AI hallucinates, so tells you something that sounds plausible and it's completely wrong, like eating rocks, right? Complex reasoning is not yet there for sure. This is the general AI is still not there. Depending on which scientist you want to believe, one tells you in 3 years we have general AI, and the next tells you it will never happen. So you can choose or just wait. There is the problem of transparency, explainability, as we discussed, but there's also another possibility, and that is the technology hits actual constraints, physical constraints. So that there's another thing that we didn't understand about intelligence, and with the system that we have, no matter how we scale it, we don't get it. It's possible. So that would be sad. I would be sad and happy, maybe because there's more research to do. Maybe it's not me though that does it. And we go into the so-called the valley of disillusionment. This is maybe you know it. It's the Gartner curve here. It's very famous for many technologies and many. They do it for every year. So the idea is that there's a hype where people say, "Oh, great! This will solve all our problems, like graphene. We will use all genetic engineering. We will decide to have one more arm like this because it's useful." Right? So you go to hype, and then suddenly you start seeing the limitations. Oh, well, it's not so easy. Here doesn't work so well. And you go into the valley of disillusionment, where basically you realize, okay, it's not so great as we thought. And then typically you go a little bit better, and it becomes like then it plateaus, right? So this is a typical thing, but there's no reason why AI has to follow that. No reason. So it's typical for human technologies, but it's not a guarantee, but this might happen.
When you talk about AI, you talk about the entire field or just language models?
You could claim for all you want. You could claim for the large language models, but you could say in AI in general. So for AI, I have much better expectations. I think there is no physical limit to it. So but this is more a belief more than I have no evidence. So I'm a person that believes that we could recreate something that is even better than what we do with our brains. But I have no evidence to tell you why. It's just my belief. But again, it's speculation. Yes.
So I've heard that the software often moves much faster than hardware, right? When it comes to AI.
Well, yes and no. I think AI is really one of the fields where they have to go together.
Yes.
They have to go together because something that will work will have to be computable efficiently. Otherwise, it's not even worth talking about it.
Yes. But then you said if the hardware reaches a peak, then would that also like lead to that?
So the peak of the hardware has more to do with the energy consumption, because the way we have it now, it's scalable, so we can build more and more, but it will require more and more power. And as you know, we don't have that much energy. So if we need even more energy, we have to finally crack fusion, or we have to find another way, because already as it is, we are destroying the planet. So that's a big problem.
Also, not everything is paralyzable either.
Well, but if you see our brain, it kind of has to be.
You destroy the planet and then you ask AI to fix.
So maybe you could claim a super intelligence cannot be achieved just with parallel computing. But I would say at least our intelligence, in my opinion, should be achievable, which is already quite nice. Okay, I just go to the last slide. So what would be my takeaways? For me, it's a great time to be alive. I'm super excited because it's one of those things where really, when I read the new progress, I'm actually really surprised. And the technologies, when I use it, feels like magic. Excellent. I like it as an engineer. If you haven't already, I think you should start learning about machine learning. It's gonna somehow be everywhere, I would think. And also get coding. And I will also, as almost a joke, don't worry too much about AI that maybe will end our life, because there's plenty of other ways that humanity can get extinct. AI is just one of the many, right? So, try to see it more like that, right? Our life is anyway limited with a very high probability, if not almost certainly. So, just enjoy the ride would be my suggestion. Okay, so thank you so much for your attention.